Hello students, in the last few lectures we are talking about the one-dimensional steady-state conduction without internal heat generation. We have solved those problems by using the electrical analogy. The electrical analogy is applicable to all the different types of Cartesian, cylindrical as well as spherical coordinate systems. So we have seen the applications of those things. Now let us have a look at some important application of the same logic, same electrical analogy, and that is going to be critical radius of insulation. Now, this study of one-dimensional steady-state conduction without internal generation gives an important aspect, important concept to us, and that concept is called as critical radius of insulation. So, in this lecture, we will be talking about this. So, in this lecture, I'll start with the concept of critical radius of insulation. I'll tell you about the relevance and the physical significance of that term. Then we'll discuss about the critical radius of insulation for a cylindrical, then for a spherical system, and we'll have a numerical problem with which we can understand the concept in a better way. This is going to be the agenda for this particular lecture. I am Nitin L. Brood, working as Associate Professor in Sandeep Institute of Engineering and Management. When we are adding insulation, normally what is the aim of adding the insulation is to reduce the heat transfer. And it happens if a simple wall is there and if we are adding the insulation, always it results into reduction in the rate of heat transfer. The reason is when we are adding the insulation, the thickness of the insulation is higher, and because of increase in the thickness, the conduction resistance increases. Now let us talk about the convective resistance. There is no change in the value of heat transfer coefficient. There is no change in the value of area if it is a plain wall, and that's why there is no change in the value of convective resistance. So what we can say in case of a plain wall, that when there is additional insulation is placed, it will increase the conduction resistance, the material resistance for the heat to flow, and because of and it will not affect actually the convective resistance. So convective resistance will remain as it is. Conduction resistance will increase, and the total overall resistance will going to be increase. So if you increase the thickness, you'll get more resistance for the heat to flow, and automatically the heat transfer is going to get reduced. But of course, this is not the case for the cylinders or spheres. However, adding the insulation to cylindrical piece or spherical shape is a different matter. The reason is because the additional insulation increases the conduction resistance, no doubt about it. Because if you are adding the insulation, automatically it will result into more resistance offered by the conduction for the conduction process. But it also decreases the convection resistance of the surface because of increase in the outer surface area of convection. If you recall that the resistance of convection is calculated upon 1 as 1 upon HA. So if we are adding the insulation, we are increasing the outer surface area, and increasing the outer surface area will automatically result into reduction in the convective resistance. Now, therefore, heat transfer from the pipe may increase or decrease depending upon which effects dominate, whether the conduction is dominating or whether the convection effect is dominating. Depending upon that, the heat transfer rate may increase or decrease. If you plot it on a graph paper, you will find that as the outer radius increases, it is plotted, the heat rate of heat transfer is plotted with along with the sorry along the outer radius R2. So it is found that it increases, the rate of heat transfer increases, reaches to a peak value, that is what is called as Q max, and then once again it starts to fall down. So this radius at which the rate of heat transfer is maximum from the system, from an insulated cylindrical or spherical system, this radius is called as critical radius of insulation. For the means critical radius of insulation is that radius of insulation where the heat transfer rate from the system is maximum, or in other words I can say that when the total thermal resistance of the system is minimum. So you can use this for finding out the value of the critical radius. So consider a cylindrical pipe. R1 is the inner radius, outer the outer radius, T1 is the constant outer surface temperature, thermal conductivity of insulation is K. Outside environment temperature is T infinity, and the convective transfer coefficient is H. So as usual our data is there. So we can express the rate of heat transfer as the uh, delta T, that is T1 minus T infinity in this case, plus the two resistances in series. One is offered by the insulation, the other one is convective resistance. We write down, and if you use this sketch once again, you can recall this sketch that the rate of heat transfer is increasing with radius and it reaches to a peak value. So the variation of heat transfer rate with outer radius insulation shows that the heat transfer reaches a maximum at value R2, at a particular value of R2, at which the slope of the curve is 0. It means that there is a particular value of R2 where the rate of heat transfer slope, the curve slope becomes 0. So we can have a differentiation in this form. So if you differentiate this equation, that is the equation of R2, sorry, Q with respect to R2 specially, and if you equate it with 0, we will get the condition for the maxima. We know the applications of differentiation. So if you perform the differentiation and if you solve this, whatever differentiation you are going to get, you can try it at your home, and if you equate it and if you solve it for R2, equate it 0 and solve it for R2, you will get the critical radius of insulation is equal to K upon H for a cylindrical system. So critical radius of insulation can be simply calculated by the ratio of the conductivity of the insulation, outside layer of the insulation, divided by the heat transfer coefficient. The rate of heat transfer from the cylinder increases with additional insulation from R2 is less than R critical, means when the value of R2 is less than critical radius, then the heat transfer rate is increasing as is shown in this. It reaches to the maximum value when the R2 is equal to R critical, that is equal to K by H, and then once again it starts to reduce when the R2 is more than R critical. So this you have to remember. Now the important question to answer at this point is whether we need to concern about the critical radius when we are insulating the hot water pipes or even hot water tanks, steam pipes, like that. So normally why we are providing the insulations? We are providing the insulation for hot water pipes or hot water tanks or for steam pipes or chemical pipes in the industries simply to reduce the heat transfer rate. So whether this, see, I told you that if the radius of the insulation is equal to critical radius, the rate of heat transfer is maximum. It is not reducing, it is rather increasing. So should we always check and make sure that the outer radius of insulation is exceeding R critical or not? Because if it exceeds R critical, then only the rate of heat transfer is going to be reduced. Otherwise, it is going to be increased. So whether it is important, let us check it. Probably not. How? Let us. The value of critical radius will be largest when the conductivity is large and H is small. It is K upon H. So largest value of conductivity and smallest value of H. So let us take the lowest value of H, natural convection. Already told you about natural convection in the introduction lecture. That and I already given you the values of the normal values of the heat transfer coefficient for natural convection when they are in presence of a gas. It is about 5. So let us take that 5 as the minimum value of heat transfer coefficient, and the thermal conductivity of common insulating material may be taken as 0.05 watt per meter square Kelvin. So if you take these two values and the large, we can calculate a critical radius by using K by H, and it was found to be 1 centimeter. Means for a simple system, if your thermal conductivity of the insulating material is 0.05 and if it is subjected to natural convection with a heat transfer coefficient of 5, we can find out the critical radius of insulation is 1 centimeter, and you can imagine, you can easily say that this is very small, and this value is very small, smaller than the normal diameters of hot fluid pipes, and if you consider the radiation, this would be even smaller than that. So as we are ignore the radiation, that we are getting 1 centimeter. If we are considering the radiation, then of course it is going to be smaller than this value. So the critical radius would be much less if it is forced convection. If the high value of heat transfer coefficient is there, H is higher, then the critical radius is going to be much lesser, often less than 1 millimeter. Often less than 1 millimeter. You can imagine. And can you have a solar water tank or solar what you call steam pipe or any other chemical pipe whose thickness or whose diameter is less than 1 mm? No. In practice, we are not using such a small diameter for carrying the fluids. Maybe for some micro heat transfer processes, it may be there. But for general heat transfer processes, normally we are preferring to have larger diameter pipes in order to reduce the losses, what you call the frictional losses into the pipes. Okay, that's why the critical radius is not a point of concern for the insulation systems. But because of much higher values of H associated with the force convection, therefore, we can insulate hot water or steam pipes freely without worrying about the possibility of increasing the rate of heat transfer by insulating of pipe, because it is normally more than the critical radius. But in case of the radius of electrical wires, may be smaller than the critical radius, because the electrical wires are having very small diameters. Okay, and that's why the critical radius of the electrical wire may be smaller than the critical radius, and it is expected, it is good that the electric wire is having less radius than the critical radius, because the heat transfer rate is going to be more, and therefore the plastic electrical insulations may actually enhance the heat transfer rate, which is a good thing from the electric wire, thus keep the steady operating temperatures at lower level and the safer level. So it is better always, if you are insulating the electric wire, you have to check that the value of the outer layer of the insulation shall be equal to critical radius. If it is equal to critical radius, it is good, because it is going to keep the steady operating temperatures at lowest possible level, which is safer. So these are the significance point for the critical radius of insulation, and we can extend the same logic for a sphere. We can calculate this critical radius of insulations for a spherical shape in the same fashion as was done for cylindrical shell, and it is calculated 2k upon h. It was k upon h only for cylinder. Now it is 2k upon h for a sphere, where k is the thermal conductivity of insulation and h is the outside heat transfer coefficient. So let us solve one simple numerical for the critical radius of insulation. Once again, same, try to solve it at your own. A 3 centimeter diameter 6, because this is a electric analogy problem. This is not a big different problem than the electric analogy. We are going to use the same electric analogy for this. A 3 millimeter diameter 6 meter long electric wire is tightly wrapped with 2 millimeter thick plastic cover, whose thermal conductivity is 0.15 watt per meter degree Celsius. Electrical measurements indicate that current of 10 ampere passes through the wire, and there is voltage drop of 8 volt along the wire. So means that electrical resistance heating is there, which with a current of 10 ampere and 8 voltage drop. If the insulated wire exposed to medium of 27 degrees Celsius with heat transfer coefficient of 12 watt per meter square degree Celsius, determine the temperature of interface of the wire and the plastic cover in steady operation. In this particular case, up till now, we have not considered anything related to the critical radius. So this is a simple problem of cylindrical system with electric analogy. We can solve this problem. Now, next point is important for critical radius of insulation. Determine whether doubling the thickness of the plastic cover will increase or decrease the interface temperature, and this answer can be given by using the logic of critical radius of insulation. So let us solve the first part. We have got the radius R1 equal to 1.5 millimeter, R2 is equal to 3.5 millimeter, converted into meter, length is equal to 6 meter, and H is equal to 12, K is equal to 0.15 for the insulation, voltage is 8 volt, current is 10 ampere, infinite fluid temperature is 27 degrees Celsius. So this is the conductor, red colored is the conductor, the blue colored is the insulation, values of R1, R2 and all these things are shown. There are two resistances, one is offered by the plastic layer, the other one is from convection. Only two resistances, both are in series. And we have to calculate the interface temperature. Here it is T1. Interface temperature means between the what you call the electrical conductor and the plastic layer. So it is T1, this temperature we have to find it out, and effect of doubling the thickness of the plastic cover. So let us do it. Assumptions are same, that is steady condition, one dimensional, thermal conductivity and the other properties are also constant. There is no thermal contact resistance, and heat transfer coefficients is also covering incorporating the radiation effects if any, and it is remaining constant. Fluid temperature also remaining constant. So all these assumptions are there. Okay, let us analyze these things. Heat is generated in the wire and the temperature rises as a result of resistance heating. So 8 volt and 10 ampere current. In a steady operations, whatever is the rate of heat transfer, it shall be equal to the heat generated within the wire. So how to calculate the heat generated? Simply the product of voltage and to current. So 80 watt energy is getting generated, and the steady condition, it is expected that all these 80 watts shall be transferred from the system. So rate of heat transfer is automatically 80 watt. So the outside surface area can be calculated as 2 pi R2 into L, and if you put the values, it is found to be 0.132 meter square. The thermal resistance, as network already has shown you, that there are two resistances in series. One is for convection, the other one is for convection. The thermal resistance network has conduction resistance and a convection resistance in series. Convection resistance can be calculated as 1 upon HA. All these values are known to us, so we can calculate 0.63. Plastic layer resistance, natural log of R2 upon R1 divided 2 pi KL. If you put the values, it is found to be 0.15. If you add them, these two, you will get the total thermal resistance. So total thermal resistance is 0.78 degrees Celsius per watt, and thus the interface temperature Q is known to us, temperature difference is unknown, R total is known. So Q and R total both are known. T1 is to be calculated. So T1 will be equal to T infinity plus Q into R total. We put the values, we will get T1 is equal to 89.4. So this is our first answer. This is simple logic of electrical analogy we have used, and for finding out the heat transfer rate first, and subsequently the heat transfer rate is being used for finding out the interface temperature. So that's not a big issue. The important question is, in this problem, we have not included the electrical wire directly into thermal resistor network because the wire involves heat generation. As there is heat generation through the wire, we cannot incorporate that wire into the problem. So that has to be treated separately. But we are not concerned about the temperature of wire. We are interested in finding out the outside surface temperature of the wire. It was found to be 89.4. Now with this data, of course, we can use the heat generation problem, and we can solve the remaining things if it is required, but in this problem it is not required. That is, the next lecture onwards we will be talking about the heat generation problem. In that you will come to know how to solve this type of conditions. To answer the second part of the question, that what is the effect of doubling of the radius, doubling the thickness of the insulation on the temperature, that is, we'll try to answer. We need to know the critical radius of insulation for the plastic cover, and critical radius K upon H, it is 12.5 millimeter. Now the what was the outer radius? The outer radius was 3.5 millimeter, and critical radius is 12.5. It means that the critical radius is larger than the radius of plastic cover in current case. Therefore, increasing the thickness of the plastic cover, as it is less than 12.5. So increasing the thickness will increase the rate of heat transfer, will enhance the rate of heat transfer until the outward radius of the cover reaches to this value of 12.5. After reaching to 12.5, it is definitely going to reduce the rate of heat flow. As a result, the value of surface temperature will decrease if the thickness is doubled. We can recalculate. If the thickness is doubled, the thickness of the plastic cover is taken as 4 mm, doubled, it will make the outer radius of 5.5. So if you take value of R2 is equal to 5.5 and recalculate in the like the previous slide, we can find out the temp through the calculation. The interface temperature is now 77.5, and this is because of enhancement of the heat transfer, and the enhancement of heat transfer is because of the radius is less than the critical radius. So all these aspects already we have discussed. So in this lecture, we have seen what is the concept of critical radius, what is the significance of critical radius for the steam pipes and the electrical conductors, and how to calculate the critical radius for cylinder and spheres, and we have solved one problem based on the critical radius of insulations. Thank you very much.